Okay, this video is going to look at our hydrocarbon shapes in the aim of improving your drawing and also answering questions about hydrocarbon shapes. So we've got a yellow syllabus point here on the top left. Analyze the shape of molecules formed between carbon atoms when a single, double or triple bond is formed between them. So this is calling back way back into module 1, that valence shell electron pair repulsion theory, that VESPA theory. Okay, and it's all about looking at how many bonding regions are around a molecule, and because they'll want to get away from each other as much as possible around a three-dimensional sphere, there's these particular shapes that form around atoms when they have a certain number of bonds. Okay, so hopefully that's starting to come back to you and we can talk about it a bit more. So when we're talking about the shape of organic molecules, we're talking really about the shape between around a carbon center. Okay, any particular carbon. We can't talk about the shape of a whole molecule unless it's really small molecule like methane, where there's only one carbon center. It's no use talking about the shape of hexene. It will be varied and in between. You have to look at the shape around each carbon. Okay, so let's choose some simple examples like this diagram I found on the internet. Very good. Alkane, we're going to look at ethane here, and we're going to look at the shape around each of these carbons. Okay, each of these carbons has 4 bonds. It's saturated alkane. The carbon-to-carbon bond and 3 carbon-to-hydrogen bonds. Now, around each carbon, there are 4 bonding regions. Now, remember the definition of a bonding region in VESPA theory was either a single bond, a triple bond, a double bond, or a lone pair. Each of those was considered a bonding region, and each of those would repel each other. Okay, so here we've got 4 bonding regions around each carbon repelling each other, and the shape in three-dimensional space around that is called a tetrahedral, and it is in 3 dimensions. So here, we've got those 2 bonds in a plane, but remember this one's coming out at us, and this one's going in, and the angle between them is 109.5 degrees. Okay, it's a 3-dimensional shape tetrahedral. So the shape of ethane, you could say, would be around each carbon center is a tetrahedral. That's how you describe the shape. With an alkene, though, a carbon-carbon double bond, so around this central carbon there's 3 bonding regions. There's the double bond, and there's 2 single bonds to a hydrogen there. So there's 3 bonding regions. And the shape that forms in 3D space is trigonal planar. Okay, so there's 3 bonds. They all exist in the same plane through the sphere, and they're 120 degrees away from each other. So here it says 122, but 120 is a good approximation there for an exam. So if you're considering the ethene here, not the old name ethylene like they've got here, the ethene, it is, both of these carbon centers are trigonal planar, and because the carbon-to-carbon double bond isn't rotatable like the carbon-to-carbon single bond, the whole molecule is actually planar. The whole of those 6 atoms are all in the same plane. Interesting shape. With an alkyne, you have to consider the bonding around it, and here we've got a triple bond and a single bond around this carbon. So there's 2 bonding regions, and they'll want to move as far away as they can from each other, and as far away as they can is 180 degrees. Okay, and so they form this linear shape. It's called linear, where there's 2 bonding regions. So when you're considering the old name acetylene, but we know it as ethine. Oh, that is terrible writing. I should write more clearer. Ethine. A little bit better. Very deep for me, though. The whole molecule of ethine is a linear molecule. It lies all along a central axis there. Not 3-dimensional at all. Okay. I think I've covered all that. Alright, let's do a couple of examples. What is the shape of the molecule named methanol, or formaldehyde is its old name, and it has CH2O. Okay. So, carbon must be the central atom here, okay? We know that carbon likes to bond with 4 different bonds. Sometimes triple, sometimes double bonds. Let's assume that there's a single bond to each hydrogen. Now this carbon is missing 2 bonds, so you should be able to guess that it's a double bond to oxygen. Oxygen loves to form double bonds too, and so this is the molecule here of formaldehyde. Oxygen's got its octet. Carbon in the center has its octet, and each hydrogen has its duet. Its 1s orbitals full of 2 electrons they're sharing. So there's the molecule of formaldehyde, or the newer name methanol. We'll learn more about aldehydes, which is the group that have this kind of thing in them. Aldehydes coming up in, I think it's the next chapter. Yeah. Anyway, shape. Around that central carbon, there are 3 bonds. So, it must have a trigonal planar geometry around there, okay? I don't need to dash or wedge anything because everything is in the plane of the page there. I'm going to say 120 degrees. So, methanol is trigonal planar in shape. Done. I like that one. All right. Explain why ethene is a planar molecule. Okay, I kind of did it before, but let's talk about it just a bit more. Carbon to carbon double bond. Eth means 2, so 2, and ene means a double bond. Fill up the rest with hydrogens. So there's ethene, and I've kind of hinted at the shape. Might as well change colour. Okay, around that carbon, and it is symmetrical, so around each carbon there is 3 bonding regions. There's the double bond and 2 single bonds. So 3 bonding regions around each carbon. Therefore, trigonal planar around each carbon. Okay, and there was that extra fact too that I don't think I mentioned in the notes, but carbon to carbon single bonds can rotate quite easily. Carbon to carbon double bonds can't rotate. Neither can triple bonds. That molecule can't rotate about that bond. If it had other stuff coming off, there were single bonds, that part of it could rotate. But these ones here. So the fact that that central bond can't rotate makes the whole molecule rigid and planar. So carbon to carbon can't rotate. Therefore, the whole molecule, those 2 planar parts are in the same plane. So the whole lot is planar. Whole molecule is planar. So each half is planar. I can't spell planar. So the 2 halves are planar, and because this central bond that connects the 2 halves is not able to rotate, it makes the whole molecule planar, which means it lies flat in the page. We don't need to dash and wedge any of those bonds. Alright, so this is all leading us we have been doing some rules about drawing hydrocarbons. And I've done the same thing as what I've done before. We've talked about this, but what I've done is updated it for all of hydrocarbons. And I've bolded any parts where I've changed it, okay? So it's just kind of what we've been doing with naming, but the opposite. We're taking the name now and drawing the molecule. So without reading all of that, let's do some examples. Hopefully I don't get them wrong. So we've got to draw this molecule here. Draw the structural formula for 5-nonene. Okay, I notice immediately, I start on the right, and I've got an alkene because it ends in E-N-E. Alkene. I've got a non here. That means 9. And I've got a 5 here. What does that mean? I'd assume, because there's nothing else, that 5 is telling me... Why am I drawing a circle there? I'm not used to this. That 5 is telling me where the double bond is. Okay. So, I'm just going to start off up the top here. I'm just going to sketch it out. If I need to redraw it to show proper geometry, I can. What I'm going to do is go, well, it's 9 carbons long. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a long one. Did I do enough? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. Whew. Always check yourself. Okay. Doesn't matter which end we start from number 1. We might as well start from the left-hand side being number 1. Okay. Why don't I change colours? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Alright, let's put some stuff on there. All we've got on this nonene, on this non-backbone, is we've got a double bond on the 5. Alright. So between the 5 and the 6, I'm just thinking here, if you numbered it around the other way, let's check if I've made a terrible error. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh. Now what I'm going on about here is, because I made up this example, it's terrible. There's no such thing as 5-nonene. It's actually 4-nonene. What a nonene I am. 4-nonene. There's no such thing as 5-nonene. It's just the same as 4-nonene. So I'm a bit of an idiot. So draw a structural formula for the molecule 4-nonene. Yeah, see, I was testing you all there. I meant it deliberately, didn't I? Anyway, 1, 2, 3, 4 up the top side is the correct way, and we're drawing the structure of 4-nonene. Okay, so what I could do is go through and put in all my hydrogens. Alright, but you can see that's going to be tiresome. We've got a long one. What I'm going to do is do an abbreviated one. So we've got a CH3 at the end, CH2, CH2 for number 3, and a CH, be careful there, double bond. Okay, so there's only room for another single bond there to a hydrogen. What I'm going to do is then show some of this 120-degree structure around this part of the molecule. Okay, that second one's also going to be a CH. Okay, and now I'm going down to carbon 6. It's now a CH2. 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 CH3 on the end. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. I'm still got nonene. So that's my what's it called? Condensed formula with my CH there's with my C and H's together. Always try to talk too fast, don't I? Okay, I might do a skeletal structure underneath. I'm going to start with the double bond and then go do it. Oh, I can draw straight lines. And that. Okay, and I've got a branch there down to that CH2, and a branch up, and a branch down, and a branch up again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. There's my skeletal structure there. Okay. Hopefully I didn't get the naming of this one wrong. Draw the structural formula for the molecule 6-ethyl-2-octyne. Ine, we've got a triple bond. Oct, we've got an 8 with a triple bond in it. And that 2 tells me that the triple bond's in the 2 position. Okay, and on the 6th position, we've got an ethyl branch. So we've got 2 carbons coming off at position 6. So we need an oct backbone. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and in the 2 position, we've got a triple bond. Let's do it from the left. I've got to, so that's between 2 and 3 there. We've got a triple bond. We can fix up the geometry in a moment. So we've got a 2-octyne and we need a 6-ethyl. So 1, 2, 3, 4, 5, 6. Here we go. And an ethyl means that there's 2. All right. So, and then I'd go through and fill it with hydrogens. Too boring for this video. Okay, I'm going to cheat. All right, I'm going to draw a condensed one. Okay, but I'm going to fix up the geometry, and the geometry around that section there with the triple bond is linear. So I'm going to fix it up. So it's going to be linear there, and that whole thing is going to be in a line there, because around those 2 carbons in the middle, it needs to be 180. Okay, and because those 2 carbons now have 4 bonds, there's no hydrogens there. Why don't I just do the fully expanded one? Okay, and so this one will now have a carbon, a carbon, a carbon, a carbon, and then there's an ethyl branch here. Okay. I just want to get rid of that last line. All right, so this one has 2 hydrogens coming out because it's got 4 bonds now. 1, 2, 3, 4. And hydrogen, hydrogen. This one here has 3 bonds, so it has 1. That's a CH2 because it already has 2 bonds. This is a CH3 because it's got 1 bond. Hydrogen, 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 and hydrogen. Okay, should I sneak in a little skeletal? All right, I'm going to start it with the triple bond. 1, 2, 3. Should I do it with straight lines? I'm sure it's going to make someone happy. Okay, and so then there's a methyl part coming off there. And oh, hang on, my geometry is incorrect. And a methyl part coming off there. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8. And from the 6, there's also a ethyl branch. All right, so something like that is good for a skeletal. Okay, next example, 1-methylbutene. All right, ene, I've got a carbon-carbon double bond. Bute, I've got 4 in that main chain, and I've got a methyl coming off the main branch there. So, 1, 2, 3, 4. I've got bute. Oh, I haven't given enough information where the double bond is, have I? Oh, maybe I didn't need to. 1-methylbutene. Hang on, this is a terrible example. You can't have a 1-methyl anything, can you? Oh, what have I done here? Where have I stolen this from? I've stolen it from a disreputable place. Is there any way that you can have a 1-methylbutene? Well, the bute will have to be in the... No, I don't think there's any way. You can have a methylbutene. Could you have a methylbutene? All right. This is like a, what's wrong with this? A butene, it could be a 1 or a 2 butene. So I'd need to know that. This is a terrible example. And if you add a methyl on there, it's no longer butene. It is a pentene. This is a terrible example. Terrible. All right. Let's see how we go with this one. Hopefully I haven't ripped it off from somewhere terrible or made it up myself in some kind of, when I've been in some weird place. All right, we've got a very long one here, but that's okay. Ene, we've got a double bond in the 2 position, and it's a hex, so it's 6 carbons long. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. We've got a double bond in the 2 position. Let's put it here. Let's start number 1 on the left to make it easy. So we've got a double bond there. Okay, so we've got our hex 2-ene. We then have, I'm just crossing out as I go along, a 2 and a 5 dimethyl. So a 2 methyl and a 1, 2, 3, 4, 5 methyl down here. Okay, and we've also got a 3 propyl, meth F prop, so that's a 3 branch on the 3. 1, 2, 3, 1, 2, 3. Okay. Alright, I was just checking there if the longest branch changes, but that's okay, we're all good, we'll keep it like that. I've taken an awful lot of space up, haven't I? Now what I do is I'd go and saturate it with hydrogens, but what I might do is leave that. Should I draw a really small condensed version down here, and I'll fix up the geometry about the double bond. So that carbon there has 4 bonds, and that carbon there has 4 bonds. So this is a CH3, and this is a CH3. Okay, and there's one coming off there, one coming off there. A CH2, CH2, CH3. And up the top way, there's a CH2, and then a CH, because it's already got 3 bonds. And off that is a CH3 and a CH3. So we've got that skeletal structure. And then that one across and 2 methyls. Alright, how did I do? Hopefully I did okay. There's a check your understanding there to do. And an end roller about the shapes. And next time, I'm going to stop it there. We're going to talk about what happens when these hydrocarbons have some halogen atoms attached. So catch you next time.